So we're ready to restart. After IPv4 comes IPv6, which we have already discovered, justified by the need to extend the number of addresses. We have an astronomical number of addresses. If we look in powers of 10, it doesn't look large, but this is truly very large. It's believed to be the number of atoms in the universe, in the known universe. But the bad news is illustrated here is that IPv4 and IPv6 are really to be seen as different network layers. So if you run both IPv4 and IPv6, that means you have two network layers in your machine. If you're a router, you need a routing table for IPv4 and a routing engine for IPv4 and another one for IPv6. And they are both using different routing tables. If you speak to a web server that has only IPv6, you have to use your IPv6 network layer. If you speak to one that is only IPv4, you have to use your IPv4 network layer. And if you are one of those guys, like A, and you want to talk to B, then it's not possible. It's impossible, at least at the network layer. You will need to find a trick. There's always lots of tricks with computers, and we will see those tricks, but it's a bit painful. The non-interoperability of the two makes the transition to IPv6 a bit complicated. So we'll talk about some aspects of that later. Notice here that the MAC layer and the TCP are not affected. So the MAC layer is the same. If you pass an IPv6 or an IPv4 packet, it's just, for the MAC layer, it's just an Ethernet frame that contains something different. In the past, in fact, this was business as usual for the MAC layer. Today, the world is essentially IPv4 and IPv6, and that's it. Those of you who are in electricity in the smart grid, you might be confronted with exotic old-style protocols that don't use IP. So you find in local area networks, for example, you had things that were developed in the 80s and 90s that don't use IP. So they use MAC addresses as global addresses, for example, because they are operating in a substation where you have only a few tens or hundreds of devices, and you never expect to connect to the outside world. There were also things that you might have heard of, like DECnet, AppleTalk, IBM, SNA, APPN, Microsoft, NetBEUI, Novel Netware, etc. There were lots of network layers that were invented and that were competing with IP. In fact, in 1992 or 93, if you had a PC, you would probably not have TCP-IP on it, except if it's a Unix machine that is, and you were probably in a university or a research center. If you would be in the business world, you probably would not have TCP-IP. Instead, you had other protocols. All those protocols have disappeared. They've been eradicated by evolution, so we won't bother talking about them. But the good news is that the MAC layer is made to handle the many protocols, so having IPv4 and IPv6 is not a problem here. TCP, in theory, and the application is also independent of the layer below. So a TCP segment is a TCP segment. Whether it fits in an IPv4 or IPv6 packet is the same. There's no difference to the TCP protocol itself. However, for the software, it makes a difference. If you're using a TCP socket in your program, if the TCP socket is meant to be used over IPv6 or over IPv4, there will be a difference for the software. Why? Well, for example, you will need to tell the operating system, I'm using a socket, I want to communicate with a remote machine. The remote machine, I need to pass to the remote machine an IPv4 address or an IPv6 address. If you have software that was made for IPv4, there's no way to give it an IPv6 address. So the software at all the layers above is dependent of whether you use IPv4 or IPv6 addresses. So just this difference in addresses means that there might be a software compatibility issue. Today, every software that is written today by a decent company is assuming that the network is either IPv4 or IPv6, so is written to both cases. In the lab, where we will ask you to write small application programs, you will do the exercise of writing for IPv4 only, for IPv6 only, and writing for something that works for both. It's a bit more complicated to do it for both, but most systems that you have today work for both. In fact, if you want to publish an iPhone or an iOS application, one of the requirements is that it must work on IPv6. It's not true for Android. So you might have an Android application that works for IPv4 only. One very famous example is Skype on Android that works for IPv4 only, or in the recent past worked for IPv4 only. So that's the bad news, and we'll talk about it later. The other bad news is illustrated here, is the length of the addresses, right? If you compare to IPv4 addresses, now this is a view of EPFL. At EPFL, we have both IPv4 and IPv6 for all the cabled systems. For example, this machine has this IPv4 address and that IPv6 address. So IPv6 is 4 times as long as an IPv4 address, so it takes more digits to write it. And if you observe here, it's written in hexadecimal instead of binary, instead of the dotted decimal. Here is the routing table at one machine for IPv6 and for IPv4. So you need 2 routing tables, one for IPv6 and IPv4, if the machine supports both. Here is, for example, an EPFL address. It is 128-bit. Half of the address is normally, not normally, but very often, half of the address is used for the host part, which means that the subnet with IPv6 is very often the first half, 64 bits. Question?
What does it mean when you have 2 semicolons, one after the other? On the previous slide, you had examples of
this one?
Yeah. Or even ED0 SWI.
Yeah, we'll talk about it. It means as many zeros as you need to. That's a compression rule. We'll come to it in a second. But before that, what I want to show is the fact that there is here a very large difference between IPv6 and IPv4, which is the benefit of IPv6. Here is the prefix. That's the EPFL prefix. So this sequence, 2001, 620, 618, 1A6, is an EPFL prefix, and the pink part is the subnet. The red part, well, the subnet is the red plus pink, and the red part means EPFL. So this IPv6 prefix means EPFL, just like 128.178/16, or in fact /15, so 128.178 and 128.179, those are the 2 blocks that are in fact 1 block of 15 bits, that means EPFL. Here for EPF4 we have this. So far there's no difference, except there is now a difference, is that the first 2001 620 means switch. Switch is the internet service providers that EPFL uses. That's the internet service providers of public universities in Switzerland. So that's a major difference. That means that because if we look at that IPv4, EPFL is 128.178, ETH is 129.132, I believe, or something like this, or 130. And 128.177 has nothing to do with Switzerland. So it is not possible to aggregate all the IP addresses of all the Swiss universities into one prefix, which means that when Switch connects to the rest of the world, Switch has to give the information to European and American and Asian and African providers of how to go towards Switch. And Switch has to inject into the routing tables of all the routers that are in the backbone of the world one prefix for every university. So about 30 to 50 different prefixes for all the Switch customers, for IPv4. But for IPv6, because we have now more space in the prefix and we have become smarter or wiser over the years, we impose that the prefix of an end customer, like EPFL, has as a sub-prefix the prefix of the provider. So 2001 620 is a provider prefix. All the customers of Switch have an address that starts with this block of 32 bits here. Which means that for the rest of the world, Switch injects only one entry. That is called aggregation. We can aggregate several sites into one because we have we reflect the hierarchy in the numbering scheme. So any numbering scheme should reflect this, but in IPv4, it's too small to be able to do that. So that's the primary difference. In IPv6, there's also private addresses. So anything that starts with FD is a private address. So there are multiple EPFL private address schemes. For example, that's the one that's used for the EPFL smart grid when we use IPv6. We'll come back to special addresses, so that's the equivalent of the 10 dot something addresses in IPv4. There are special rules for human beings to read IPv6 addresses. IPv6 addresses need to be written for example, when you manage a network, you allocate the addresses, so you have to somehow manipulate them. It's not only the machines and the routers that manipulate them. And if you have an address like this one, right, it's very nice if you can compress it. So the rule is that the double column represents any number of zeros. Right? Of course, you can find it only once, because if you have it twice, you don't know how many zeros go in every place. So you know that an IPv6 address is 128 bits. That means 16 pieces, where a piece is a word of 4 hexadecimal digits. Then so you know the total number, so you just pad by as many zeros as required. Typically, we write them in lowercase, the digits, so lowercase a, not capital case A. The decimal digits don't have uppercase, but the letters do. And if any piece starts with zeros, you can omit them. So this is visible here, where you have 0620, you can write it as 620. So you will need to add a 0 here to make it visible. I read it as 2001, like everybody does, and in fact, this numbering plan was standardized in 2001. That's why it's called 2001. IPv6 emerged in was standardized in 1997, I believe. Then it went through many iterations of standardization of the allocation of the numbers, and this was done in 2001. But this is wrong, in fact, because this is not 2000. This is an hexadecimal number, which is much larger than 2000, because it's 2 times 16 to the power 3 and not 10 to the power 3 here. But everybody does it, so I'll do the same. There are special addresses. The 2001, in fact, anything that starts with 2 or 3 is a global unicast addresses. Those are the blocks that are allocated today. Blocks that were used before 2000 were the 4000 blocks that were used also, were allocated in 97, I believe. But they are normally not used today. Everybody believes that IPv6 is the last version of IP. So in 500 years from now, we will still be, other people, will still be using IPv6 addresses, but you might allocate different blocks, 2, 3, 4, 5, etc. We have seen those different addresses here. So we see that 2001-620 is the common prefix of this provider. EPFL and ETH are 2 special cases of those. Swisscom has its own block. And then you have special blocks. The 2002/16 and as many zeros. That means everything where the first 16 bits are exactly 2002 are special addresses that we use for what is called 624. Those are some addresses that we use in the lab. There are addresses that are used when you do not have access to IPv6 internet, but you still want to run IPv6. We'll talk about it in detail a bit later. Then there are the special addresses very similar to IPv4. But as you can imagine, now that we have practically unlimited address space, everybody find a good reason to have special allocation of special addresses. So there are zillions of special cases of IPv6 addresses, not literally zillion, but many. And here are a few examples. As usual, zeros everywhere means absence of address. The loopback address is not the weird 127, but it's simply 1. So zeros everywhere, except the last bit, which is equal to 1, which gives also the hexadecimal digit 1, means this host. So it's the loopback address. And /128 means there is only one address. It's not a block, it's a single address here. Then you have the equivalent of the private addresses are the FC and FD something. So the FC 007 bits, which means the first two valid digits are FC and FD. Those are what I mentioned before, the private addresses. You can do whatever you want with them. Then you have the link local addresses, which unlike IPv4 are very frequently used. IPv4, we use link local addresses only if you have Windows running at home and connected to nothing, and it still will find an IP address, but in practice, it's not able to connect to anything outside the local area network. In contrast, in IPv6, the link local address are always used. For example, if we look at this routing table here, when a router has a routing table that gives the next hop, it will typically give the link local address of the next hop. So every IPv6 address always has a link local address plus a global address. That's a difference we find with IPv4, where in principle one interface has one address with IPv4. With IPv6, one interface always has, or most often has, two addresses, and sometimes more, as we'll see. One which is link local, and another one which is a global address. For example, an IPv6 host at EPFL always has an address of this type, plus it has an address that belongs to this block. We will see how they are used. Those link local addresses are a good or bad idea, I don't know, but they are part of the complexity of using IPv6. Multicast address exists like with IPv4, and they have this special FF00 prefix. Then you have special multicast addresses that we will see in a minute. And you also have the equivalent of the local broadcast, which is the 1, FF02, lots of zeros followed by 1. That means link local means inside the local area, a broadcast to all systems that are in the same local area network. And the same with the 2 instead of 1 means to everybody who is a router, not to any system, but only to routers. Yes?
Are we expected to memorize those?
Yes, of course. No, I'm joking. So the question is, are we expected to memorize that? No, of course. There's no point memorizing that. I will publish towards the middle of the course what is called the exam booklet, but you can look on last year's edition what did the exam booklet look like. At the exam, you don't have documents, but of course, things like this will not, I will provide you with a copy of the documents that provide this information. Here's the IPv6 packet format. So the first large difference is the size. The source address now is 128 bits. Typical convention at IETF for writing packet formats is by words of 32 bits. So 4 bytes is 1 line. And now an IP address, IPv6, is 4 lines. So the IP header is in principle 20 bytes. The IPv6 header is in principle 40 bytes. So we double the size of the header. Other than that, the things are very similar, except the protocol type is now called next header. It means the thing that comes next, as opposed to protocol type, but we can use them as synonyms. One of the drawbacks of IPv6 is the length. For example, if you use IPv6 to talk to your smart thermostat using Bluetooth that has packets of size with payloads of 20, 40 bytes, or things like this, then even an IPv6 packet doesn't even fit in Bluetooth. That might be a problem. So for special cases like this, there has been what are called packet compression mechanisms. So if you run IPv6 on Internet of Things devices, you will use what is called compression technique. So you first establish a connection between the two links, the two ends of the links. This is typically done by Bluetooth, for example. And then you agree on compression rules, because very likely on this link you will see a very small number of IP addresses. So you can first establish a dictionary of IP addresses, and instead of sending the source an IP address, we can say it's the first address in the dictionary, and this is the second address in the dictionary. So if you have a dictionary of 8 addresses, you need only 3 bits to describe an address. That's called compression, for example. But apart from those smart Internet of Things kinds of things, we will need to pay for the price for this larger header. Sometimes we will need to juggle with the representations. For example, in places like EPFL, where we have both IPv4 and IPv6, if you want to manage the network, I mean, EPFL is 10,000 people, so about as many computers and as many IP addresses. So the guys who are in charge of the network, they need to simplify their job as much as possible. So what they did is, for example, that the IPv6 address contains the IPv4 address. So if I have an IPv6 address at EPFL, the last 32 bits somewhere in my IPv6 address are the same as in the IPv4 address. So if I see an address somewhere, I don't need to map one to the other. If I see the IPv6 address of this machine, I know exactly what is its IPv4 address. That's the kind of luxury we have at places like EPFL, where we have both. Normally, you don't have both IPv4 and IPv6. If you have, why do you normally not have both? Well, what's the motivation for having IPv6? You don't have enough addresses. So if you have enough addresses, which you do if you give an IPv4 address to everybody, you don't need IPv6. IPv6 is a pain. It's like having a system that works both for Windows and the Mac. It works, but with considerable expenses and effort, and once in a while it crashes. There's always a function that doesn't work well. So you need to rederive a lot of software if you want to be compatible for both. We did this experience with the smart grid of EPFL, where we developed everything for IPv6, and every 3 months we had a concrete problem that needed patching and some that we would not have had with IPv4. So that's common experience, I believe, that many people have. I hope in 10 years from now it will be the opposite, and people will say, oh, I tried to do it in IPv4 and I had a lot of pain because I had to use lots of old things that don't support the new versions of the kernel, etc. But today it's the opposite. So if you have IPv4, you don't need IPv6. But if you don't have enough addresses, you have to have IPv6. But then if you don't have enough addresses, you cannot have IPv4 everywhere. So this special case of EPFL is for the kind of transition places where we do IPv6 because we want to be good citizens, but in reality we don't need it. In cases like this, you may need to write addresses in the same form. For example, we will find IPv4 addresses written in this form. So if I match that to the normal way of writing IPv4 addresses, which one is it? So I hear the question, at the exam, will I have to transform IPv6 addresses from decimal to dotted decimal? If you have to, that will be completely obvious things to do, because you're not expected to have a computer. I close the poll. And of course, it's the first one. Here it was an easy catch because the second one is invalid, right? You recognize 255, which is all ones, and the 393 is above 255, so it's not a valid one. And if you want to check, of course, you take your calculator. Another question? If I want to write the hexadecimal notation for this string, how many bits should I find? I close the poll. That one is easy too. And the correct answer is, of course, E. By convention, any string of that type is a 28 bits. Of course, it's a 28-bit with lots of zeros here. And of course, B, A, B are hexadecimal digits. So the theory of IP is fairly simple. However, there is a weird thing that has emerged very quickly over the years that was not at all anticipated by the designers of TCP and IP. It's called the NAT. And that's very symptomatic of what happens in networking, where you have an architecture, a design, and then something sneaks in, and then it may become important. So we'll see several of those things in the course. What is a NAT? A NAT is something that we all have, probably at home. The problem that is solved is that if I am connected to Swisscom's internet services, Swisscom gives to me one IP address. And at home I have printers, computers, smartphones, several people, so I probably need 10, 20 different IP addresses here. So how do I use 20 different computer equipment with one single IP address? In principle, you should not. That violates the TCP/IP architecture. We've seen that an IP principle is every interface has an IP address. So it violates it. So it's used, as I said, very typically, invariably in all ISPs. All ISPs give to you one or a block of address, which is typically much less than all the addresses you need. EPFL being an exception. At EPFL, all the 128, 178 addresses that we have are globally valid IP addresses. But if we would redo it today, if EPFL would start today and would ask for a provider to have an address, to have some IP addresses, they would give, from IPv4, they would give a block of perhaps, I don't know, 100, 1,000 IPv4 addresses, and then EPFL has to find its way with that. It's also used, for example, in smartphones when you do tethering or connection sharing, where, for example, you use your smartphone to connect to the 4G network, and you use it at home as to connect your printer, not your printer, but your laptop or a friend's smartphone that does not have 4G, for example, which is, in fact, playing the same role as the modem, the ADSL modem or the Cablecom modem that you may have at home. Right? So what it does is, in particular, it allows you to have more than one address at home. And if you use addresses that are not given to you by an ISP, the only choice you have is to use private IP addresses. So invariably, when you are at home, you use addresses that are, for example, 192.168 or 10 dot something, depending on how your system is configured. So how can we go from an internal network, my home, to the global internet by using addresses that are not valid in the global internet? Well, we need to translate those addresses. This is done by a box called Network Address Translation, which again violates the IP principle. I mean, we went through 2 or 3 quizzes where I asked always the same question: what's the IP address of the packet we see? And it's the IP address of the destination. But here will not be the case. If I receive from a web server a packet that goes to my device, in the internet, the destination address will not be the destination address of my device, because my device has a private address and it's not valid for a web server that's out on the public world. It doesn't know which to send. Probably all of us have similar addresses. So all of us at home have a 192.168, 10 or 0. Those addresses could be at any of our homes. Right? So we have to do something. The reason is that what I said before did not work, is that the box here is not a router, it's a NAT. Now, about terminology, people will call it, I called it an ADSL modem. People will sometimes call it router. Sometimes they will call it your Wi-Fi base station. The name of a box is very often misleading. It is the commercial name, or the name we use in everyday life, has to do with the most visible function of that box. If it has antennas, you call it a Wi-Fi base station. If it has a big plug coming from the telecommunication line, you call it an ADSL modem. But in fact, it is doing a number of functions. ADSL modem is a layer 1 function. Router is a layer 3 function. Wi-Fi is a layer 2. It probably does all of that. And what it certainly does is, in addition to all of this, it does the NAT function, Network Address Translation Box. So see, it doesn't have a nice architecture name. We call it a box. What does it do? Well, it does a trick which consists in modifying the IP address of the source when a packet goes from So what I call on the left the private network is, in the terminology of NAT, is called the LAN, the local area network, and the public internet is called the WAN, the wide area network. So if I have a packet that comes from the LAN and wants to go to the LAN, I have to change its IP source address. And the IP source address that I can have is only one, is the IP source address that is given to my provider, by my provider to me. So I give this address. So in this direction, it's easy. But the problem is in the reverse direction. If those two devices are given the same IP address when they go out, when the response from a web server, for example, comes back, how do I know it has to reach A or B? I have a collision because I've given the same address to two devices, which defeats the purpose of addresses. For that, we need a trick. The trick consists in overloading the port number used by UDP or TCP. It's a complete hack in the sense it violates all the layering. We have a box that, in order to forward a packet, looks at two layers at the same time, IP and transport layer. This is what a NAT does. It's ugly, right? But it's smart also in some sense. For example, here, the NAT must have what is called a NAT table that says that all the packets that on the LAN correspond to this address, 10.10, which is the A machine, and the UDP port 1029, which is UDP port used for whatever, I don't know, perhaps for going, it's a local port used for going to the DNS, is mapped on the public internet to this address, that's the address that is given to me by my provider, and a port number, which is 3441. B, which uses the same port number, but has a different private local address, of course, will be mapped to the same IP address, but a different port number. It works because there are many, many port numbers. The port numbers are coded on 16 bits, and typically a machine uses a few port numbers, perhaps 10, perhaps 100. So with this trick, you can multiplex close to 100 different machines on one single IP address here. This is implemented by a trick in the NAT, which is called the IP tables, if the NAT is Linux, where essentially the NAT being running in software, does IP forwarding in software, has the possibility to do what is called pre-routing or post-routing. That is, before or after forwarding an IP packet, you can manipulate all the fields in the IP header. This is what is possible if you, and trivial, not trivial, very easy to do if you have a software router like we have in the lab, for example. And this is how NATs are typically implemented. So when a packet comes from, for example, a response from a DNS server to here A, it will have a port number and IP address of the NAT, and a port number that was allocated only for A. So, sorry, 3441, so that's address 11. That's a bug in my animation. I should go to A here. I think you should mix up the things here. How is this correspondence created? Of course, you can do it manually. You can tell, or you can go with, if you find a user manual of your ADSL modem, you can log into the ADSL modem using HTTP, and then you will have a menu where you can write those mappings. You do that, but that's an extreme case. If you had to do, I guess none of you did it, and it still works at home, so there is an automatic way to do it. And this automatic way consists on doing it on the fly by sniffing all the traffic that goes from the LAN to the WAN. So for the first time that these guys open a TCP connection to this server here, the LAN will observe this. It will see from this address and this TCP port number. If it's the first time it sees it, it will create an entry in its NAT table by finding an available TCP port number that was not used already, and it will remember it. It needs to remember it, of course, for when the response comes in the reverse direction. This has a drawback, though, is that for this to work automatically, it requires one thing. This thing is that the communication is initiated from the LAN. It is LAN that must start the communication, which means the server is on the WAN. If the server is on the LAN, so if you have a web server at home and you want to post it on the internet, then you have a problem. You have to solve that problem in a way, but the NAT alone doesn't know it. So one way to do it is to manually, as I mentioned, go into your NAT and make this configuration. But in practice, most of the time, this is not done. What is expected instead is that the applications, that like Skype or other applications that may be peer-to-peer, need to work around this. So the NAT has been designed with the idea that behind the NAT in the LAN is something that goes to a server, and the server is not behind the NAT, the server is on the public internet. If you do peer-to-peer communication, like a Skype call, this won't work. But it works with Skype, because Skype has done a number of things to fix the problem. The very first versions of peer-to-peer voice over IP required that you go into your NAT and configure it. There was a Microsoft Net meeting, for example. So it never worked. You needed to be an expert and have taken this course to be able to use this software. What Skype does typically is that it involves a third party. So when you do a Skype call from home to behind the NAT to someone that might also be behind the NAT, what your Skype software does is contact a Skype server that is not behind the NAT, and the Skype server will see what is the IP address that you have, because you don't know your IP address, right? When your host, your Skype machine, well, you think that you have this IP address, but for the rest of the world, you have that one. It's also one part of the things that make the difficulties caused by the NAT. So typically, you need a third party that is not behind the NAT, and solving that exactly is required for peer-to-peer application. A small question. When a NAT has a packet to forward and an association exists in the NAT table, what does the NAT do? I close in 5 seconds. And the correct answer is B, of course. Another question of the same style. I close in 5 seconds. And it's B again, here. From one to LAN, the NAT may modify the destination port, and in the reverse direction, the source port. Of course, the NAT is making the assumption that the traffic is TCP or UDP. If you create your own transport layer, it won't work because of the NAT. In fact, that's one of the problems that the communities face today. Companies like Google, for example, that cause a large fraction of the total internet traffic. They're not happy with TCP, they're not happy with UDP, they'd like to change it, but they can't change it because of NAT. If you do a new transport protocol, I mean the Google Transport Protocol, the GTP, the NATs, they will not know about it. You need to wait until all the NATs are changed. So of course, you have a problem. It's called the ossification of the NATs. The NATs are really, because they're outside the architecture, they violate the architecture, they put a lot of limits on what can be done. So in practice today, if you want to invent a new transport protocol, which we will see, there are many attempts to do that, you do it over UDP. So you do it like an application layer protocol that is an intermediate layer protocol that is truly a transport protocol, but you make it UDP so that it has port numbers because of the NATs. I will conclude with the network masks. Yes, question?
How does NAT play with ICMP? It doesn't have a port number.
Good point. So we will see a bit later that there is a an IP protocol that does not have a port number. It's called ICMP. That's the set of error messages for the IP network layer. So if a host is unreachable, we respond with an error message saying host is unreachable, and this is ICMP. Well, the NAT needs to analyze specially all those ICMP messages. So it has a software that does a bit like the pretty printing software of when we observe a packet trace. It knows all the ICMP error codes, and it analyzes them and translates them. A good NAT. A bad NAT will ignore them, and your ICMP messages are lost. Yes?
What layer does ICMP work at?
What layer does?
ICMP work at.
At which layer is it?
Yeah.
Well, that's a religious question. I try to avoid being in religious affairs. Many people will say it's layer 3, but on the side. It's the control protocol of layer 3. I mean, we've seen sometimes people say there is the main part, which is the data plane, then there is the control plane, which are things you do to manage, to control. There's also the management, which is almost the same, but a bit different. So many people would say it's layer 3, but this numbering of layers is, of course, a simplification. This is why in IPv6 we call it next header. We just say inside an IP packet there is another packet, but the numbering of the layers is perhaps too strict to be easy to follow. I will quickly conclude on the masks. We've seen this last week. So a mask is needed because all hosts need to know in which local area network they are. And when a host A has a packet to send to B, the first thing it normally does is know whether I should use IP or I can natively send by finding the MAC layer, the MAC destination address. And for that, I need to have the mask, which is simply expressing the number of bits. At TPFL, the mask is 24 bits. At ETH, is 26. And at IPv6, in most IPv6 networks, it's 64 bits. And we've seen the only difficult things on the mask is understanding why we have this clumsy notation with 255, 255, etc. Typically for IPv6, we will say, for example, this is a snapshot of the configuration in Windows for IPv6. It will ask what is a subnet prefix length. This is in IPv4 terminology that would be called the network mask. In IPv6 terminology, sometimes some source system also call it the mask, which is the same as giving 64 bits of ones followed by zeros. So in IPv6 notation, this is how we would write the mask. Voilà, that's all for today. See you tomorrow at 11:15 sharp.